Roger on that? Going okay?
I might have broke it again.
You kind of broke it again? What happened?
I don't know, the second run when you change the spherical albedo,
Yeah.
I'm not getting any data out. So I've got an appointment shot with Monica.
Did you change it with tape 5 editor or did you change it by hand?
With a tape 5 editor.
Okay. Did you take a look at the file afterwards, make sure everything changed the way you thought it might? There's only one term that you changed there.
Yeah, and it's just the albedo. Yeah, I don't know why it, like I said, I'm going to talk to Monica later today.
All right. Now, what I want to do, we've gone through systems, and we have a good feeling for how all these different systems work and how we can calibrate a system itself. In other words, so we can take the radiance that's reaching the front end of the sensor and can convert that to a known value. All right, so we have energy that reaches the front end of the sensor, it's recorded as a digital count. Now we can convert that digital count to a radiance value, an absolute value. All right, now that's what you would call sensor calibration, right? Being able to convert that energy entering the aperture of the system into an absolute radiometric quantity. So what I'd like to do now for the next couple of days is to talk about a term that really goes under a lot of different names, and there are very subtle differences between them all. So you'll hear terms like atmospheric calibration, atmospheric correction, atmospheric compensation. Right? You'll hear all those terms, and then we'll actually introduce another term here that we call atmospheric normalization, which is probably over the past 15 years or so starting to get used a lot more within the remote sensing community too. So I will at times slip between those terms, and in reality it really doesn't matter what you call them as long as you know what you're doing. But I'll try and stick with the right terminology for that. All right, and I'll try to point out as we go along what might be the subtle differences. All right, so the object in remote sensing is to take the recorded signal that your sensor produces, whether or not that's a digital count, a voltage, density on film. You name your imaging system, pick your modality. It's going to produce a value based on the energy that's entering the object. The idea then is to relate that recorded value back to an observable object, something that you're interested in. Okay? So if you look at the beginning of chapter 7 in the text, it goes through this little bit of an exercise here that I think is worth going through before we start to look at actual atmospheric calibration techniques that we'll do in a couple minutes here. Because it is something that does work at times, and a lot of people, and I mean a lot of people, if you read through the application literature of remote sensing, people who do use remote sensing as a tool to come up with a answer, for instance, what is the biomass of this forest? How much fuel is there underneath the canopy for a forest fire? What's the chlorophyll content in a particular body of water? There's lots of people who, to them, that's what remote sensing is, and those are the applications. Those are why we here in the center's remote sensing program try and make the tools and the sensors and things that we do is to really help out the application folks. But if you look at the mass of literature out there, it's dominated by applications. Now, I don't want to say that folks who do applications aren't doing remote sensing correctly, but there are a lot of papers where that is true. And it may not be for any reason short of they don't understand this one simple concept. That if you have some parameter that you're trying to study, soil moisture, biomass, fuel content, chlorophyll concentration, you name the parameter. It could be some function of the digital counts that you're recording your sensor. Okay? And you can write it, y equals f of those digital counts in your sensor. All right, well that's great. And if you go through and you look at that a little more closely, you know, you might have a sensor that has multiple bands, a hyperspectral sensor, or in this case, a 3-band sensor. Well, I'm sorry, it's an N-band sensor, there's no ellipsis there, there should be an ellipsis there. And then you have multiple observables. So for instance, let's say I go down into my scene, and I measure the chlorophyll content of the water at one location. Then I take my boat, drive to another part of the lake, and measure the chlorophyll content there. And then do the same thing, drive to another part of the lake, measure the chlorophyll content there. Do it in several, you know, locations across the lake, or do the same thing in a forest if you're looking at biomass. And I record those Ys, right? So Y sub I are each of the observations that I might make. And then I look at the digital counts that I record in the sensor. Well, I can come up with some function, right? It might be a multivariable linear regression, like shown here. It could be a logarithmic, you know, regression where you're with logs and terms. It could be some, you know, form like this where you're taking the ratios between bands. But essentially, they're all linear regressions. And what you come up with at the end is some predictive model. You come up with the coefficients, A in the first case, B in the second case, the vector C in the last case. You come up with those coefficients, and you can predict from your observed digital count values Y with some error. Okay? Now you've done this hundreds of times, right? You've taken data, you fit a linear regression to that line, and you said that was your answer. But what did you always do before you said, let me do a linear regression and come up with the equation for a line for this data that I have? What was the first fundamental thing that you always did?
Do you assume that they're correlated?
There has to definitely be a correlation between the data. You always plot the data, right? And make sure it's a line. Right? I mean, this is a very fundamental thing that I'm going to try and get across. And so you want to look and you want to find that relationship. A lot of people will just take the data, throw it in a Minitab, and come out with an answer. Right? That's fine. You get a nice predictive model, and it works great for the 10, 12, 15 points that you actually measured. But then if you try to use it on some other point in the scene, it falls apart. And you know, hopefully you've never fallen into that trap, but I'm sure you probably have at some point. I've done the same thing. All right, so coming up with that fundamental relationship is important. All right, now, what else can you see? I mean, you've been in a remote sensing class for 4 weeks now, right? And you've been in an imaging science program for 4 months, 5 months. With what you know at this point, what do you see fundamentally wrong with this sort of approach?
Just off the bat, it just seems too simplistic. Like, it doesn't take into account anything. It doesn't take into account any kind of orientation or clouds or atmosphere.
So none of those parameters that we tell you to worry about are in here. In fact, they're all in there. Right?
Yeah.
Because those digital counts have all those effects built into them. Right? Those digital counts are acquired through an atmosphere, through a degrading optics, through a noisy system, you know, through all the problems that we have. It's all built in there. So this approach actually is probably the best you could ever do. All right, so I showed it to you first. Why go on? If this is the best you could ever do, and I want you to, that was a good answer, but now turn that answer around as why do we want to go on?
Well, you want to factor in what the error is. That's a big question, right?
Well,
Like, you want to understand it perfectly to figure out the error.
you would like to understand that error. But if you have enough data, well, let's look at the last case here, where you have C0, C1, C2, C3, C4, and C2 to the n coefficients. If I had 2 to the n plus 1 points for observations that I made on the ground, what would my error be? What's that?
It would be bigger than if it was just a couple points.
No.
So
So let's go back to a very simple case, a straight line, y equals mx plus b. I have a naught and a1, right? So I should say a naught plus a1 times x. If I had 2 points, what's my error in my regression coefficients? 0. Right? So if you have as many points or as many observations as you have unknowns in your equation, your error is actually going to come out to be 0 for the data. The minute you go off of it, you can have a really big error in your prediction. So I just want you to keep in mind these, really fundamental concepts, which a lot of us forget all the time. All right, so if y is going to be perfectly predicted or very well predicted, let's say we're using the top equation there, where we have a naught, a1, a2, an, and let's say we have 10n points. So we have 10 times the number of observations that we actually need to solve for these coefficients exactly. And we do a least squares regression, and least squares comes out great. The correlation comes out to be very high. The R-squared values, 0.99. All the beautiful things that you want. Let's say that all happens. You have a really good confidence in your model at that point. Right? Now, what happens then if I fly my sensor again a week later over the same area and I apply these same equations? The model is no longer valid, right? The atmosphere changed. The view angle might change. The solar illumination angle might change. Leaves might have fell off the tree, right? I mean, all kind of things physically could have changed in the scene. So while this model is the best you can possibly do for any one particular flight, it's not extendable to multiple flights. Okay. So when I say, if you look at the remote sensing literature and you see the many papers that do the same exact sort of thing, those papers are really good. And it's a really good experiment that they did at that one location. It's just not extendable to another day, another collection geometry, another time of the year or time of the day. Does that make sense?
So you need to come up with a model for every location, for every...
Ideally, you need to come up with a model for every flight, for every... So I like what you just said too, every location. Because let's say the observations I made were all over the scene. Is the atmosphere homogeneous over your whole scene? No. So this starts to fall apart even at that point, because it's not homogeneous. You're using this one model, but it's really spatially variant throughout your scene. So lots of issues come up. All right, thanks. I'm sorry, I was sitting away from the mic there for a second. All right, so to get away from this, we're going to take a step back. We're going to look at the big equation that we've been working with all along, and we're going to try and figure out the parameters in that big equation. Because if we could do that, if we could figure out what the atmospheric transmission is, what the upwelling radiance is, what the downwelling radiance is, all these terms that are inside of that equation, if we could figure all those out independent of observation, well then we can possibly relate digital count at the sensor down to ground leaving radiance. Right? And ground leaving radiance can then be related back to the reflectance of the target. And the reflectance of the target is some physical characteristic. Right? And if we could do that sort of thing, then I think we have a better approach. So what I'm talking about here is, with your sensor calibration, what we've done so far, we know that the digital counts that we record are some function of the radiance. The radiance is some function of the reflectance on the ground. Right? The observed parameter, biomass, chlorophyll content, you name it, is some function of reflectance. Right? Same as radiance. All right? So hopefully we could get through all this and still come up with this relationship, but have it be based upon more fundamental physical principles, namely the parameters that are there in the energy propagation equation. All right. So you could do this kind of thing, that we just talked about. You could do it in the reflective region, right? We can measure solar photons that get reflected off targets at the sensor, a digital count related back to the actual observable. You could do that in the thermal, right? For that matter, I could set up a bunch of pools at different temperatures. You see the thermometers are at different heights. Pretty nice image. Right? You could set up those pools, and you could then go ahead and measure something adjacent to it, right? And maybe get a temperature. So, for instance, if this pool, let's see, this pool's the coldest. This is in the middle. This one's the warmest. Right? So I have 3 different temperature pools. I'm applying a thermal sensor overhead. I can record the digital count values for each of those. Right? Water has a very high emissivity. It tends to almost be a black body. Many people assume it's a black body. And emissivity, looking at a nadir position, is around 0.986 for fresh, clean, distilled water. Right? So it is very, very high. So if you assumed it was a black body, then you can go ahead and measure something else in the scene. All right, so let's say this is supposed to be a river, okay? If I measured the river, can I come up with a temperature? Well, if I knew the temperature of each of these baths, I could fit a function through temperature as a function of digital count recorded on the sensor, right? So I can plot digital count on the vertical axis temperature on the vertical axis and digital count on the horizontal axis, and from these pool observations, and then I can look at the water in the river, and if I get a digital count, I can come back with a temperature. Right? That's fine. Right? That's the same sort of approach that we were just talking about, but again, it only works in this one instance. Right? It only works for this one atmosphere and geometry. I'm not going to say time of day in this case because we're looking in the thermal infrared, so the solar photons are not important in this case. All right, so that works, right? But again, you'd have to have these pools in every scene. Now, don't think this is silly. If you go up onto the 4th floor into the roof lab, I have 3 10-foot by 10-foot kiddie pools that I keep up there, right? We inflate them for every experiment. We put them on the roof. We fill them with water, and we put them at different temperatures. This is an awesome way to go ahead and look at things. Now, here's the problem. What if I want to look at something besides water? Right? I know the temperature of the water here, and I assumed they were black bodies because the emissivity is very high. I look at the water in the river, its emissivity is also very high. It's water, right? And for all intents and purposes, it's probably a black body. It's probably 0.986 again. It doesn't vary all that much as long as you don't change the view angle. So everything's okay. I'm looking at the same sort of a target, the same emissivity. I can come up with a temperature value. Well, what if I went off and I looked at the ground? Say this is concrete. Its emissivity might be 0.9 as opposed to 1. And now that relationship, the direct relationship between temperature and digital count no longer holds because the emissivity has changed. So I need to be a bit careful there. All right, so one step you can take to go a little bit further is to not actually record temperature of these water baths, okay, but record radiance. All right, so take a radiometer rather than a thermometer and look at the surface of the water in these different pools. So now my relationship won't be between temperature and digital count. It'll be between radiance and digital count. Right, now that's a subtle difference, but it's very important because now I could measure the radiance coming from the river, and I can convert that to a temperature. Right, I could take that radiance, divide it by the emissivity to increase the radiance. Right, because the radiance that you see from any surface is always going to be lower than the Planck black body equation indicates that it will be. And so you divide by that emissivity, increase the radiance, take that radiance backward through the Planck equation, you can come up with your temperature. Okay? But now the nice part is I can go over here on the concrete and do the same thing. Right? I have a radiance to digital count calibration. Well, this is just radiance, this was just radiance, this was just radiance from these 3 points. as long as I know the emissivity, I can then back out, through the Planck equation, the temperature of the object, as long as I divide by that emissivity before I do so, and increase that radiance time. So it doesn't matter if I'm looking at a black body or a mirror, for that matter, a very low emissivity part. Okay, so those are the sorts of things that you always got to keep in the back of your mind. I just did an experiment in August. Shame to admit this. I put out the kiddie pools and I measured temperature. And then, we brought all the data back, and I could tell you this because she's not physically on campus anymore. But one of my grad students, Sarah Paul, has this data now, and she's about 2 months away from finishing up and starting to write her dissertation. And I realized that we did this, and this experiment, this data was for her thesis, and I haven't told her yet. Right? So this is one of those questions we're saving for the defense. So we're sort of sadistic when it comes to defenses. Right? So we'll save up that one key point. I need to tell her at some point because I don't want her to totally mess up everything. I have to go back and redo answers. But I'm going to let her sweat a little bit longer. But we just did this, and we messed it up. So always, if you're ever doing a thermal experiment, go back and read the beginning of chapter 7 in this book. I don't care how many times you do a thermal experiment. I've been doing thermal experiments since the mid-1980s, and I screwed it up again. So go back and just refresh yourself with this stuff because they're all really important points. And the most beautiful part is myself, Mike Gartley, who does a lot of thermal experiments also, John Schott, and we're on Sarah's committee. We all sat in a room and listened to her experiment, and it wasn't until weeks after that I realized we did it wrong. And I know John didn't realize we did it wrong. And I know Mike didn't realize we did it wrong, so we all forgot it. All right, so I think it's one of those very subtle things that you got to be careful with. So keep that in mind. This is the beginning of this particular chapter is definitely worth looking over many times because we captured it at one point when we were thinking about this stuff. All right, so a lot of times we design systems such that they react in a linear fashion. And that's good. It keeps life very simple. So the relationship between digital count and radiance falling onto a sensor is often linear. Right? Everything's designed so that these sensors respond in a linear fashion. And the other beautiful part is that the reflectance is typically linear related to the radiance leaving that surface, based on a bunch of factors. Right? But in most cases, that relationship remains linear. There's certain scattering properties that will result in nonlinearities, and in fact, almost all scattering properties are going to result in nonlinearities, but they're very small. The nonlinearities are small, so we get away with it. The answers that you often get from a remote sensing problem, as scientists and engineers, you've always tried to get the perfect answer. Right? You've always tried to say, okay, well, I know in this case that y is 14.6. And you always strive to make sure it's 14.6 plus or minus 0. And you always try to get that 100% answer. One of the things you have to realize in remote sensing is that there's so many variables. There's so many things that go wrong. There's so many things that you just don't know that you're never going to get that 100% correlation in this equation. You're never going to get an error that's 0. When we work in the reflective region of the spectrum, we're very happy if we get the reflectance of an object to within 5%. Right? That's good. That's like a NASA quality calibrated sensor. Right? Something that we fly around here, we're happy if we get to within 6%, 8%. When we're looking at temperatures, when we look at temperature of water, because water is a black body, we strive for the couple tenths of a percent, the 0.3, the 0.4 of a percent, degree error. So if we can get to within 0.4 Kelvin or half a Kelvin, we're pretty happy. When you start getting temperatures of land-based targets, things that aren't black bodies, then temperature error goes up because now you have imprecise knowledge of the emissivity of the target, unless you know exactly what the emissivity of the target is on the ground, how do you ever get to the exact temperature? And my question for you is, how do you know the exact emissivity of the target on the ground? Right, that's a very tough thing to get. I'm actually writing a proposal this week where we're looking at trying to model contaminants on the surface of a material. So yesterday, before it rained, I went outside and I was taking lots and lots of pictures for the proposal of salt stains on the ground. As you walk around, you'll see footprints and tire tracks and all that kind of stuff drying on the ground. Well, look at it really carefully next time you're out there. It's asphalt. Let's say it's on the asphalt walkway. Then there's areas where there's a little bit of salt, and you can still see the asphalt through it. And then there's places where the salt's so thick that all you're seeing is salt. And then there's other areas that are brighter than they were in the summer, but you really don't see any patterns of salt there, but you know there's a fine dust all over the surface. If you went down and you licked the ground, it would probably taste like salt, right? This is real ground truth, right? So when you do that sort of thing, and you notice those sorts of things, then you come to realize that if I went to ever measure the temperature of the asphalt right now from a remote sensing system, how would I do that? Right? I measured the emissivity of the asphalt on the sidewalk out there 100 times. I know what it is at the time that I measured it, but it's not what it is right now because it's a contaminated surface. So hopefully we'll win this proposal. Be right about the time when you guys start to look for projects. So hopefully it'll be a neat modeling project to try and predict those things, because it's impossible to measure all those possible combinations. So we need to somehow get a physics-based approach at actually modeling what the emissivity might be. But coming up with that emissivity is critically important. So that's why for hard targets, for solid surfaces, it's often very hard to get a good temperature. Okay, so in the end, what we hope to do is to get to some sort of relationship like this. But I hope I've convinced you now that this empirical approach, this one sort of Schott experiment, isn't all that valuable because you can't extend it. It's valuable if you can have people on the ground every time you fly your plane overhead. Right? I have the good fortune of being able to do that because I have access to all of you. Right? So every time we do an experiment, we send all of you out into the field. In September, you're all probably going to be out in the field, right? Because we're planning an enormous experiment with a dozen different sensors flying overhead for the September timeframe of this year. But we don't always have that good fortune. And if you're trying to do remote sensing in an area that you can't get to, then obviously you can't measure things on the ground. All right, so it's not always possible to go through this, and it's expensive. It's very expensive to try and ground truth something. Yeah.
So you know how people use ground truth of like water in the desert or ice caps or something like that to try, but then we were saying that even within a scene, it's still variant. So
Absolutely.
I mean, even being at the Libyan desert and then having something in the corner, knowing what your ground truth site is supposed to look like and knowing it pretty much never changes, it's still not that good.
Well, I don't want to say it's not that good, but let's say we use the Libyan desert as a reflectance state, or as an emissivity state. It doesn't change over time for all intents and purposes. But if there are winds that blow, then the texture of the surface can change some. So that texture change or slight change in slope of that surface can change the emissivity, but it's very subtle. How do you know what the reflectance of those sands should be? Well, you know what time of day that you collected an image. You know what day of the year it is. Astronomers know exactly where the sun is at those times. So if you know where the sun is and you know it hasn't changed its distance from Earth and you know its temperature probably hasn't changed all that much, I mean there's some nice constants in the universe, right? Those are some of those things. Then you should know the amount of energy reaching the edge of the atmosphere. The unknown is between the atmosphere and the ground. Right? What happens to the solar energy between the top of the atmosphere and the ground? Well, it's going to get attenuated in some way, scattered. You're over a desert, so the atmosphere is very stable, doesn't change all that much day to day, but it does change slightly. Right? So so the errors are minimized when you work in areas like that. You know, for instance, we calibrate the thermal channel of the Landsat sensor here. Why is that? Because we have a Great Lake, right? We know the temperature of the surface of that lake. We can go out, we can measure it. It's a big body of water, good target. We don't do the reflective bands of the sensor. Anybody know who does the reflective bands of Landsat? We're at the University of Arizona. Why is that? They're in the desert, right? So they have a big target that they can use to do the reflective portions of the spectrum.
So do you use that, if you, like say you go around and you see the Libyan desert like once every so often,
Yeah.
then do you use that radiance to DC conversion for the whole time until you get back to it and you can re-evaluate it for
You
the
have to.
Libyan?
You have to.
Okay.
Yeah. So if you're temporally observing a target and you have some period of time and you can measure it on day 1 and measure it on day 10, in between you can either use what you figured out on day 1 for those 10 days, or you can wait till day 10 and go backwards and interpolate. All these things are, you know, anything you do is going to be a fudge, obviously, because you don't know what actually happened. And so you have to always be careful. And this is where you have to build up an error analysis so that you can say, here's your answer, plus or minus 3.6%, or you know, be able to put something as far as a quality factor or quality metric on an estimate.
But I mean, any system is like looking at water pretty often, right? Water's covering the globe, whether it's like an ocean or a lake or something like that. So can't they just be constantly calibrating with water?
You gotta know the temperature of where you're looking.
And that's not really well documented, at least in the United States.
Well, there's a series of buoys spread all over the major lakes. There's buoys in the ocean. They measure temperature. All right, you're really getting on my sore point here. This is good. All right, so you have water. You have a buoy. It's a buoy. All right. Tell me where you're going to measure the temperature.
Surface of the water?
All right. So you're going to put how are you going to do it? You want to put a thermometer there, right? All right. So there's equivalents, or there's lots of different ways you can make thermometers, but the most common is something called a thermocouple, right? It's two wires of dissimilar metals that are joined together, and when you join two metals or two dissimilar metals together, they form a potential across there. And if you do a weld on that joint, if you change the temperature of the weld, you can actually change the resistance across that weld, and it's proportional to temperature. Right? So it's a very simple device that you make. Get a copper wire and a Constantine wire, weld them together, and you have a temperature measurement. That's all it takes. All right, so let's say I put that thermocouple right here. All right, what's going on in the ocean? Waves, right? The buoy's going down. There's a bell up here, right? It's ringing, right? And sometimes I'm measuring the air because it goes up this way, and sometimes I'm measuring a foot under the water. All right. What do you know happens on the surface of all water bodies?
Isn't that where the mixing goes on?
Well, there's mixing going on from the waves, so water from deep comes up and splashes over and it spills in. Okay. What else happens? What happens when water and air meet? What goes on in that interface? Evaporation, right? And when you go from a liquid state to a gas state, there's a big energy consumption. So the water at the surface is actually cooler than the bulk water that you see underneath. When you look into thermal infrared, you can only see a couple molecules deep in the water. Those couple molecules are at a much different temperature than the bulk water. But that's what you see. So what you want is you want the temperature of this surface. You want the temperature of the top couple molecules of water. I don't know how to measure that. All right. Now, believe it or not, I don't know if you've seen the research magazine that just came out recently, but there's a picture of John on his kayak, right? So this is ground truth. John goes on his kayak, and we have this little piece of styrofoam right? And on the bottom of the styrofoam, there's a thermocouple glued to it. And then there's a wire that goes into the kayak and you hook it up to a voltmeter. And you measure the resistance. All right, great idea. All right, you put this piece of styrofoam on the top of the water, it tips over, right? It goes up and down, it blows in the wind, and that's how we measure temperature of the surface. That's wrong. It's just not right. You can't do that. What you need to do is you need to be in situ with a radiometer and measure the radiant energy leaving the top couple molecules. All right? So you need to be here with a radiometer of some sort. Okay? And measure not temperature, but radiance due to the temperature. Then you can invert that back to the flat body equation to get the temperature if you want to.
Is that too expensive for a buoy system, or?
Yeah, so that's where it comes into play. We recently finished an experiment out at a power plant in Michigan where we were trying to measure surface temperature on a cooling lake. And we built 5 big buoy systems, and on those buoy systems we put radiometers at each point. Well, radiometers don't like to be outside for extended periods of time, like 2 years. And seagulls come along, and they poop on your radiometers. Water splashes on your radiometers. It's a cooling lake, so there's hot water, it steams. Water condenses on your radiometer. Now it's measuring water on itself. And then the radiometers, even when we bought them in the lab, drifted as a function of time. So that was the $150 radiometer. Figured I didn't want to lose I have a nice FTIR that would work very nice. So for a transform infrared spectrometer, that would make very good measurements, but you have to be there in order to make them. You can't do it in an automated fashion, and I didn't want to put a 60K sort of instrument on a buoy. My guess is, well, then the lake froze, and we crushed buoys and crushed equipment and ice, and when ice starts shifting around, it's pretty heavy. It ruins things and crushes things. So yes, it's way too expensive to put radiometers. So the only good way to do it is to be locally and measure with radiometer. Now there's a mid point in price range, and there's these things that they call infrared thermometers, and you'll see them. You can go over to Sears actually and buy them, right? That people, they call them heat guns. You pull the trigger and you get a temperature. Wow, that's great. Except that when people use these things, they point them at a piece of aluminum and say, the temperature says. Well, it doesn't take into account the emissivity of the aluminum. It's only taking into account the radiant energy coming off that. So you have to be very careful. Some of the more expensive ones, you could dial in an emissivity, and they'll adjust for that, but you have to know the emissivity. So it's an extremely hard problem to measure the temperature of water. The easiest thing in the world that you think might happen is very tough to do.
But you can measure pretty stable the temperature underneath the water. I mean,
absolutely, underneath the water, not a problem at all. And so what a lot of people have done is they've come up with surface temperature models.
Right.
So if you know the bulk temperature, then you can predict what that surface temperature is going to be. But it depends on a lot of things, but there are things you can measure. It depends on wind speed, relative humidity, all the environmental parameters need to come into that. The problem is, you measure wind speed up here, but on the surface of the water, you have Reynolds forces that cause the wind speed to decrease. So I'm 30 years into my career and I still can't measure the temperature of water. Right? So that's my goal. Before I die, I want to make that contribution, but I still don't know how. All right. So thank you for setting me off on that tangent. Let me just check the question in a second. Yep, okay. So many problems, but let's assume we can make that measurement at this point, because then we're just going to be here talking about that for the rest of the quarter, and we're never going to get anything done. All right, so if I want to come up with an ability to measure temperature, then I could just take the big equation and let's just look at the thermal components of it for a second. So we have the black body radiance due to temperature of the water. We have the transmission of the atmosphere to the sensor. And the radiance reaching the sensor L is going to be that the temperature due to the black body nature of the material itself, times the transmission up to the sensor plus the upwell path radiance. Okay? And if you look at that, it's a nice linear equation. All right, so there's a little bit more to it than that. All right, if it's not a black body, it's not water, then you have to add the emissivity term in here. Right, so you have to take your black body radiance for a target at a certain temperature, multiply by its emissivity, efficiency factor, and then propagate that up through the atmosphere. But now, since it's not a black body any longer, it has some reflective component to it. So you need to reflect the downwelling radiance, and then propagate that up through the atmosphere to the sensor, and then add in your path radiance. Now again, you can look at that as a simple linear equation, right? Where the energy coming from the surface, LT, over here, and I apologize, terminology isn't really fantastic in the text. This LT is different than this LT, right? Because this LT is the sum of both the self-emitted radiance, epsilon times LT over here, plus R times LV, the reflected radiance. So this is the radiance leaving the target. Okay. Now, built into all that is the transmission up to the sensor. So your M here, if you look at this carefully, if you plot this right, if you know the radiance leaving the surface, LT, then your slope is your transmission, and your path radiance is your intercept term. All right, so if we go back to the black body assumption for a second, so we're working with water again, you can invert this equation really easily to find LT. Radiance you observe at your sensor minus an intercept divided by the slope. So in other words, take off the upwell radiance, divide by the transmission, and then you have the radiance leaving the ground. Assume you went through a perfect atmosphere. All right, then you can invert that to come up with water temperature. All right. Now, at that point, you can start to group these things together, and it becomes a little clearer. That's what I just said on the previous slide. And now, if you have a non-perfect black body, you have a target that has an emissivity less than 1, you need to come up with another way of solving for that surface leaving radiance, right? In this case, it's going to be the radiance leaving the surface itself. That's the sum of both the reflected and the self-emitted energy. Right? You need to subtract from that the reflected energy, so you just get the self-emitted energy. And if you have just the self-emitted energy at this point, divide that by the emissivity, and you can come back to LT, which in this case, I just want to make sure, it seems to change throughout the notes there, unfortunately. In this case, it's the radiance leaving the target because of the target's temperature itself. Because we backed out that emissivity term and subtracted off the reflected downward.
So that L0 or L0 is supposed to be the LT from before.
Yes. Yeah, it's the it's that LT. Yeah, that LT. Okay. Does that make sense? All right, so let's take a look at a problem for a second. All right, so if we go back, I'll just move this over so you can see everything. All right, I like this equation here. So let's start with this one. All right, so if we have L equals tau 2 times epsilon LP plus the reflectance of that surface, or 1 minus epsilon if it's a solid surface, times the downwelling radiance plus the upwell path term. Okay. So if you expand everything out here, like it was in the previous slide, essentially you have tau 2 epsilon LT plus tau 2 R LV Okay, and the question becomes, if, well, let me go one more step and just put everything in terms of univocity here. So you have tau 2 epsilon LT plus tau 2 1 minus epsilon LD plus 1. All right, so now everything's in terms of the target emissivity, and make the assumption here that the target is solid. There's no transmission going on. So Kirchhoff's law says we can do 1 minus epsilon. All right, the question is, how important is it to know LD? All right, so in other words, if we look at this term right here, the reflected downwelling gradients that gets up to the sensor, tau 2 times 1 minus epsilon times LD. If we look at that term, how critical is it to our final answer here, and eventually our final derived temperature here? How important is that? All right, so let's just take some typical sorts of numbers for a second. LD, all right, the downwelling gradients in the thermal region of the spectrum, compared with the temperature or the radiance leaving a target at ambient temperature. So let's say Earth ambient's around 300 Kelvin. Figure out the radiance leaving that, it's about 9.8, at about 10 microns, it's about 9.8 times, or 9.8 watts per meter squared is a radian micron. Right? So you get a number around 9.8 watts per meter squared at 10 microns. If you look at the downwelling radiance, just, and this is a ballpark, you know, at any point on the Earth, you know, let's take the average downwelling radiance. It's about 1/5. Right? So it's around 2 watts per meter squared radian micron. All right, so it's about 20%. All right, so if I asked you, can I just ignore downwelling radiance? Well, if the downwelling radiance is 20% of the signal that's leaving the ground, at that point it sounds pretty important, right? All right, well, let's take a little closer look at that. All right, now, if you think about what a particular material is and what its optical properties are and what its emissivity in particular is going to be, most things in the world are fairly high emissivity, right? Polished aluminum, not true. That's a fairly low emissivity. Aluminum foil, low emissivity. Gold, low emissivity. Right, but these aren't things that you usually find laying around everywhere, right? If you look at grass, if you look at asphalt, if you look at concrete, if you look at trees, if you look at things like that, their emissivities are fairly high, right? I would say most things in the world are 0.85 and greater as far as the emissivities go. It's rare to see something, you know, around 0.4 or 0.05. Gold is way down there. All right, so let's take an average. Let's take a 10% reflector, or 90% emissive object. So if I look at this equation here, if my emissivity is 0.9, right, so fairly high, that value becomes 0.1, okay, reflectivity. And LD is about 20% of the LT, the radiance leaving the target. So 0.2 times LT. And then the transmission up to the target itself, tau 2, is going to remain constant. Okay, so let's just leave that as a variable for a second. All right, so...
You mean L naught?
L naught. Depends where we're looking. In this equation right here, it's LT.
So that's...
It's that term right there.
So that's 20% of... Okay. Of the self-emitted.
The downwelling radiance, LD, is about 20% of the self-emitted for a 300 Kelvin black body. All right, so what do we have? We have 0.02 tau 2 LT. All right, so at this point, the reflected downwelling component, you can see, is 2% of your total signal. Okay. All right. So I can ask you the question: if I compare this value with this value, and it's only 2%, how do you feel right now if you don't know LD exactly? You don't feel all that bad, maybe. You know, if you don't know it at all, you're going to be 2% off. Well, if you want to get an answer that's down around a couple tenths Kelvin for your temperature, then 2% is big. If you're working on absolute scales, if you're working on a Kelvin scale, 2% of 300 is how many degrees? Right? 6 degrees or something, right? So you're off 6 degrees, that's a big error. All right, so 2% is not something that you want to live with. All right, but now let's say I measure the downwelling radiance. Right? Now I know it exactly, now I'm not 2% off anymore, I got a great answer. But it's very hard to measure downwell radiance. How would you measure downwell radiance from the atmosphere? Well, you have to have a radiometer on the ground. You have to have some sort of cosine integrating optic on that, so it takes energy from all directions and directs it onto your sensor, and you come up with a downwelling radiance value. It's a very tough measurement to make, especially in the infrared, because your optic has to be some infrared transmitting material that refracts just properly to do that collection. All right, so it's possible. I don't own one of these instruments, and they're actually not all that common, right? They do make, actually, I'm sorry, I do own one of these instruments. They're called PIRs. Made by a company called Epley. We have one upstairs. I apologize. So you can measure this. You can place it out there and you can measure the downward energy. But you don't always have that location where you're trying to measure. So if you're doing a ground truth experiment, you obviously can get that. All right. But in general, you don't have that. So how else do you get the downwelling radiance? Or by next Thursday, how are you going to get the downwelling radiance? Right? You could run something like Montran. Right? Montran can give you a prediction of the downwelling radiance. Right? Montran needs inputs. Montran needs to understand the atmosphere. So at your experiment site, if you can launch a radiosonde, a weather balloon, and record temperature, and pressure, and water vapor content, and sure, those three things. If you can launch that at your site, then as a function of altitude, you can know how much water vapor is in the atmosphere. You can know the concentrations of the ideal gases based on the pressure in the atmosphere at that location. You can know the temperature of your atmosphere. And if you put that input into Montran, right, in the form of a radiosound card deck, which you can, you didn't do it in this exercise, you just chose one of the standard atmospheres. We'll come back to that in a second. If you can put that in, you can get a very good estimate doing exactly what you're doing for this lab of the downwelling radiance curve. Okay. If you don't have that radiosonde, it's very hard to launch a radiosonde at your site. And if you do launch it at your site, it's only at your site for about a minute until the wind blows it one way or the other. Right now, it's not even over your target anymore. So you're getting sort of this vertical, or this angular profile of the atmosphere. All right, what's the next best thing? Well, the next best thing is to find 2 or 3 airports that surround your experiment site, get their radio sounds, and interpolate your data back to that location where your experiment's going on. If we launched a radiosonde at Rochester, which we don't, and we launched one at Buffalo, which we do, and I was in Batavia, and I'm doing geography again, I think Batavia is between here and Buffalo. What are the chances the weather is going to be a linear interpolated value between Rochester and Buffalo and Batavia? Right? You look at the weather all the time, and there's storms coming this way, and clouds are over here. It's never the same. So interpolation is very tough. All right, but the next best guess is going to be to use one of the standard atmospheres in Montran. So you choose mid-latitude summer. Great. I don't even know where that is. Right? So, but that's your best choice. All right. So the question is, how accurate do you need to be? Right. So let's say we only get our downwelling radiance to within 10%. Montran's been around for a long time. I think if we had a radiosonde or even interpolated radiosonde data, we could probably get our downwelling to within 10% or so. A 10% error on this term is now going to multiply this by 0. It's going to move the decimal place over here. So our error term, I'll use E for error, I don't want to use epsilon, that's lucidity. Our error term is now 0.2% of the actual value. All right, so if I get my downwelling radiance to within 10% of the actual value, I'm only going to make a 0.2% error in my final answer. That you can probably live with, because there's plenty of other things that you're not going to know that well. So while downwelling radiance is important, you can't ignore it, but you could put up with some error. So, just something to think about if you do thermal experiments. All right. Now, all right. That's great. We measured some things in the scene. All right, I measured some radiances leaving the ground. I measured those same radiances on my imagery. Get back here for a sec. So if I measured some radiances on the ground, the LTs, and I measured some radiances at my sensor, L, I can plot those points. Hopefully I get some data that shows some nice correlation. I could fit a regression line through that. I'm going to start that again. Right, let me do that. I'm going to draw my line first. All right, so I had some LTs, and I had some Ls at the sensor, and I had some points that I measured on the ground, and I have an intercept over here. I want my intercept to be positive, right, because that's my upwell radiance, and my slope is my tau to the sensor. All right, that's great. We can do that. We can derive those two terms. So now we can use those terms anywhere. We can then go ahead and run Modtran and come up with an LD term. So then we can go back to this equation, and we have all the answers. We have LU, we have LD, we have tau2, we have L, that was measurement we made at the sensor. So for any point in the scene now, for that measured point, we can come back and solve for LT, provided we know the emissivity of the target. So now, I do that, and I do that every time I collect, every collection, I derive those parameters, and all my physics relationships hold. I don't have to rely on that atmosphere remaining the same or anything like that as we did in the original example. All right, now, you don't always have that luxury of being on the ground. In fact, you almost never have the luxury of being on the ground, except when you're doing an experiment to prove that a technique works. So, the next step is to not use measurements, not use ground truth, but be able to try to use something inside the scene itself to do calibration with, right? And these techniques, you've probably seen the term before, are called in-scene, obviously, which would be stuff in the scene, calibration techniques. Right, so doing in-scene calibration is 95% of the way that imagery is calibrated, because we can't do that. Now, here's the unfortunate part. There's probably 50 different in-scene calibration techniques out there that have been put in the literature over the years. Starting back in the late 1960s through yesterday, there's a calibration technique that's come out. I'm assuming it came out yesterday. But you see them very, very often. So why? Why have there been so many?
Depends on what you're looking at and what you're looking at.
Well, it depends on a lot of what you're looking at and when you're looking at it. So there are great calibration techniques that work great for water. There's other great calibration techniques that work great for forests. And there's a lot of scene-specific sorts of things. That being said, there's only so many things that people look at, right? So you think, there would at least be, a couple, but there's always a problem with one of these techniques, right? So a lot of times what you'll see is somebody comes up with a great new calibration technique, they do an experiment, they prove that it works really well on their experiment, then they publish a paper, And then somebody picks up that calibration techniques and tries it in their slightly different situation and it doesn't work all that well. So they modify it, come up with a new calibration technique, do an experiment, publish it, and then it just keeps propagating. Things keep changing like this. And today, there is no single calibration technique out there that everybody's going to agree on. Okay? So what I want to do is I want to show you a couple different ones that are sort of indicative of the classes of calibration techniques that are out there. But there's many variants on it. All right, so we're going to look at 4 in particular. We're going to look at something called a multiple altitude technique. Where this involves looking at a single target on the ground from multiple different altitudes in order to characterize the atmosphere. Okay? So you're looking through different atmospheric paths, and because of the different path lengths that you're looking through, you can come up with some good answers about the atmospheric parameters that we're going to try and solve for. There is a multiple angle technique, right, where you're going to look through different angular paths from the same altitude at the same target. So you look at it maybe straight down, and then you look at it from, let's say, 45 degrees. Now you're looking through 2 different atmospheric paths, and we can back out tau and LU from that. There's also a class of techniques called multiple band paths, where you would look at a target through 2 different sensors that have different band passes. So you might, the 8 to 14 micron window that we usually do thermal infrared remote sensing, and you might break that up into, let's say, 8 to 10 and 10 to 12, and look at a target in those multiple band passes and be able to back out the atmospheric parameters that way. And then the last one is radiation propagation models. So things like Mach. To be able to do this. All right. You want to take a break? Great. Let's take a couple minutes. That we saw are techniques that we've actually done. All right, so they're papers that folks in the lab here have published over the years on doing calibration. I'm not saying these are good compared to other techniques or better in any way. We're just familiar with them more than anything else. So the first technique that I want to look at is an example of the multiple altitude technique, and it's something that in the literature is often referred to as the profile. Okay. And the way this proceeds is as follows. You pick several targets on the ground that are going to represent different spots on the ground that will emit different amounts of radiance, ground-leaving radiance. So you want to find targets that are either drastically different temperatures or drastically different emissivity. All right, because between emissivity and temperature, you can adjust the radiance leaving the ground. So if you can get some sort of series of targets on the ground that vary in radiance, ground-leaving radiance, that's the kind of targets that you want to look for. All right. Typically, what we do is, in order to fly at various altitudes, you have to have a very clear flight plan file. And it turns out that it's very easy to do this sort of a thing where you fly an aircraft at many different altitudes over a single target when that target is at the airport. Right? Because everybody can see you, they're watching what you're doing, and they're happy. And at the end of runways, there's these beautiful big numbers painted on the ground, and they tend to be very different temperatures when compared with the rest of the runway. Because a lot of times these letters are sometimes they're black, sometimes they're yellow, if I'm not mistaken. And the paint absorbs differently, so it absorbs more solar energy, and certain parts of the ground heat up more than the others because of the way you treated that surface. So you can get some different radiances that way, and normally there's some grass nearby that you can also look at. And so you can get 4 or 5 different points on an airport very easily that are different temperatures. All right, now, once you do that, and once you identify those targets, you fly your aircraft at multiple altitudes. And then, for each of those targets, at each of the altitudes, you plot the radiance that you observe at your sensor. Okay? So in this case, that would be L at some height, H, and at a viewing angle of 0. Okay? So LH of 0. And you plot those radiance values, all right, as a function of flying altitude. All right? So this target on the ground that was emitting about 5.1 radiance units here is emitting slightly less as you went up to about ½ kilometer, slightly less as you went up to 1 kilometer, slightly less 2, 3, 4, 5, 6 kilometers. You name the number of altitudes that you want to fly. But as you get higher and higher, typically the radiance gets smaller and smaller because the transmission gets lower. Right? The path radiance also gets greater. Right? So it is possible for the radiance to increase, but typically the path radiance increases at a rate slower than the transmission decreases. So the radiance typically falls off as a function. There's certainly situations where that's not true, but typically that's the case. And the more radiance that you have leaving the ground, usually the curves will become steeper. So these are exaggerated the way they're drawn here, but you'll see these curves get a more steep slope as the target on the ground is warmer. All right, so if you do this, and you can do this at every altitude, well, you can come up with this fantastic data, all right, that you could do something with in a second. But there is a problem. It's hard to fly at 0. Right? So typically what happens is you fly down as low as safely possible. And usually they don't let you fly lower than 500 feet over the airport. So you can fly down to about 500 feet or so. And then what you do is you fit a line to these points and extrapolate it down to the ground. Right? So you're going to obviously get some small error, but if this data is fairly well behaved, hopefully that error will be small. And what you do then is you get your radiance leaving the ground value from an interpolation. All right, so great. Now we have this data. We have radiance as a function of altitude for different targets on the ground. Now, eventually, I'm going to be flying at the height that I want to fly at. All right, so let's say 6,000 feet. Let's say that's the final altitude that I'm going to actually do my remote sensing, collect that. I can take the radiance I observe at that level, and I can plot it versus the radiance leaving the ground. Okay, so, oh, there's a picture. Well, an equation. I can plot the radiance at altitude, and if I'm looking straight down, theta is 0, so LH 0, as a function of radiance leaving the ground. Right? This is just like we did before. But before we were on the ground measuring radiance, and we were in the plane measuring radiance. Now we're in the plane measuring radiance at multiple altitudes, and figuring out what the radiance leaving the ground was based on fitting these functions. Okay, so this is the equivalent of being on the ground with a radiometer. And if you believe that these relationships will hold, right, they hold to within some error. You're not going to see a drastic shift in the shape of that curve. Right? So you're going to get pretty darn close to what your value should be leaving the ground. Then you can figure out your tau and your LU using linear regression. Right? Because you have multiple observations of LH0 right, for your different targets, different emissivities, different temperatures, but varying radiances. And L00, you have many different values. Here there's what? 9 different ones shown. So you plot those versus one another, figure out the slope and the intercept, and you get your tau and your LU. And you're done. Right? That's the profile thinking. Very simple, right? Kind of a neat concept, and very easy to compute. All right, now, that works great for looking straight down, but now you got to say, okay, but most of my targets are not going to be directly under my plane. They're going to be off in my field of view somewhere. There's sort of going to be some angle away from the sensor in the aircraft that's not going to be 0. So I need to figure out tau h theta, and the same thing's going to be true for the path radiance. LUH data, right? But we have approximations for that. If we go back to the previous section, or last quarter radiometry, you know that the transmission changes as a function of the angle. So you trace the secant theta. And the path radiance, or any radiance at an angle off nadir, is going to change, divided by cosine, or multiply by secant theta. So those should be some approximations. If, right, the big if here, if you assume that your atmosphere is homogeneous, right? Your atmosphere has to have the same particles everywhere where this can hold true. So changing path length, you can modify your tau and your LU based on changing path length, which is what those terms are, if you assume your atmosphere is homogeneous. All right. Now, we have tau, we have LU, we don't have LD. Okay? So LD is the next thing we want to try and come up with. All right, so work with me here for 1 sec. Let me write out 2 equations. If I observe a target from off nadir, so at some height and some angle, and I look at a target on the ground, I know its emissivity is a function of angle, so I have E sub theta there. Black body radiance, just the big equation components, so the self-emitted terms, the downwelling terms, and the path radiance term. Okay? And if I look at that same target, straight down from nadir, so a theta is 0, all the terms change to reflect that in the same equation. All right, now, this radiance and this radiance will be different. Right? If I look at the same target on the ground through a bigger view angle, the radiance are going to change because the path radiance and tau are going to be different at those 2 points. But LT, the radiance leaving the target in the vertical direction or straight up, is going to remain the same. All right? LD, for falling down on the ground, is going to remain the same. All right? So I can solve for LD, bless you, if I take these 2 equations and rearrange them in such a way that I can equate them on LT. All right? So essentially solve this one for LT, solve this one for LT, equate the rest of what's left, and then solve for LD. Right? It works. I did it last night on my kitchen table. It went here, it went on to here, and there was one more. I'd call my son down at one point because I couldn't figure out a trig theorem, but and I finally got the answer, and it actually turned out to be pretty simple in the end. But you can go through and solve that, and now from that same data, what do you know? Well, let me give you my final answer here. Turned out that LD equals epsilon theta, emissivity, times L at an altitude and a 0 viewing angle, minus LU, the path radiance, the same condition, all over tau and H 0, and then difference in the emissivities. All right, minus something that looks very similar but with the opposite components. So E naught, L, H theta, minus LU, H theta, tau, H theta, and that same term. Or epsilon zero. All right, so LD turned out to be that. If you read through the text, there's one sentence in there that says you can easily compute LD. It does tell you how or what the final equation is, but it does refer to a paper. This paper here called Temperature Measurement of Cooling Water Discharge from Power Plants, right? Put out in 1978. They put it out on the site here. It's right here. This guy. And it's not 2003. I put the wrong date. It's 1979. I'm sorry. So I'll change the date there. But the paper's out there for you to use. And some weird terminology. I don't know what W was, but essentially that was radiance. So just, terminology is a little bit different than you saw in radiometry class. But he finally comes down to this equation right here, WS, which is the skylight. And he has slopes in here and some R terms, which are reflectivities. I kept everything in terms of emissivity. So I've gone through the rigorous proof of this, but I think this equation and this equation are exactly the same if you just substitute the right terms in. Right? Because you can see M here is this ratio of E naught over E theta and tau of H naught, or H naught and H theta. So I think if you substitute all that in, you come up with the same final answer. So you might do that as an exercise. That might be a really awesome exam question. You might go through that as an exercise. Derive that equation from these two, and see if you can get to the equation in Schott's paper. That 79 from it. I think you could do it. It was between the time when my wife started cooking and it took me through cooking and just slightly after dessert. So it took me, I don't know, maybe we didn't have much. I think it was macaroni and cheese or something like that. So cooking wasn't long. So it was about half hour sort of exercise. All right, but you can get there. But that's pretty awesome, because what you wind up with, if you look at that equation, is you know everything in here. You know LU, you know tau, you know the emissivities, maybe, right? And then you can compute LD. All from just observed data in your scene. No in-scene ground truth collected at all. Everything's just from the aircraft itself. And so really sort of a very attractive technique. Now, are you going to get within the 10% for LD? I don't know. You have to do some experiments to figure that out. But it's going to depend on a lot of things. It's really going to depend on your knowledge of the emissivity. And emissivity changes as a function of U angle, BRDF. And so you have to have a good knowledge of how that changes in order for this technique to work very well. Beautiful part, title of the paper, Cooling Water Discharge from Power Plants. Water is very well understood. You can look in the literature, you can find the angular dependence of emissivity on water published out there, a bunch of them. And so E theta and E naught for water are very easy to come by. The other stuff, you just need to make the measurements. All right. Profile technique makes sense? All right. Simple technique, works great. We do this all the time. We fly at multiple altitudes all the time and correct our imagery this way. All right, so sort of an example. If you're looking at Lake Ontario and you wanted to map temperature on the surface, you can do the profile technique in a couple different places. I don't even know where those squares are. That's like over Sodas Bay, and that's somewhere between here and Buffalo. I don't know what that is. But I don't know why they chose those locations for this particular paper that they did. But they were able to go ahead and map the thermal bar on the lake from a satellite-based sensor. So what they did in this case was they flew the profile aircraft, they flew the aircraft at different altitudes underneath a satellite collection. So if you can correct the atmosphere underneath the satellite, well, then you can extend that calibration up to the satellite and you're in good shape. What does that imply? We were just talking about this at the break, right? You gotta keep flying because H needs to be the altitude of your sensor. So you gotta keep flying that altitude so you just pass by the satellite, right? In order to get the true tau and the true LU. Not always easy to do. You gotta fly high enough that you have good faith that the rest of the atmosphere above you doesn't really matter. So if you can get up to 10,000, 15,000 feet, when do you have to start using oxygen? Around 15,000?
15 or 20 probably.
Yeah. You fly until you start getting dizzy, then you come down. All right, so now let's shift gears here for a sec. Multiple view angle techniques or multiple angle techniques. Here, we're going to make the assumption that, again, our atmosphere is homogeneous. And we're going to look at the same target on the ground through two different paths, where the angle, or the view angle, is going to change by this angle theta. If you can go through and have that be an assumption that you have this homogeneous atmosphere, then you can come up with a pretty cool approach using multiple angles. All right, so I can write two equations for radiance reaching the sensor. LH theta is tau h theta, transmission through that path at that angle to that altitude, times the radiance leaving the ground in that direction, plus the path radiance. All right. And then vertically viewing, where the theta is 0, looking straight down, I can come up with an equivalent equation. Okay. So for a Lambertian surface, okay, you can go ahead and eliminate the surface radiance term and equate everything together, because the surface leaving radiance in a particular direction or straight up, if it's Lambertian, is what? Yeah, it's the same. L00 is the same as L0 theta. Okay, those two are the same. So if you can equate these equations based on these two terms, you can wind up with a solution for the radiance reaching the sensor at a particular angle is a function of the radiance reaching the sensor looking in the nadir position, straight down. Right? And then if you look how everything's structured here, your slope, if you plot these values as your x terms, or your abscissa terms, and your ordinary, your independent variables as the radiance reaching the sensor at some angle, your slope's going to be a ratio of transmissions along the path, and your intercept term is going to be this combination of path radiance through some angular path, straight up, and that same ratio of transmission terms. So if you look at several targets on the ground, you'll get several different radiances at an angle, several different radiances straight down. You can plot those two things as functions of one another, and you can come up with this ratio, and which is your slope, and this summation over here, which is your intercept term. All right, now there's your slope and your intercept, and what we'd like to do is be able to come up with our transmission and our path radiance in the vertical viewing direction, right? Because in the end, we want to look straight down at the scene, right? So if I look straight down and I look at an angle, I want to be able to come up with the tau and LU term in the nadir looking direction. All right, so there's a big jump in the paper, or in the text again, where go from these equations to this equation that says tau in the vertical viewing direction is the slope to the 1 minus secant theta minus 1. Right? And LU is the intercept over secant theta minus the slope. All right, so let's take a look at that for a second, because I think that's a pretty big jump. All right, so we had M equals tau h theta over tau h0. Okay, looking straight down. All right, I can rewrite that, right? I can say M equals tau h theta times tau h naught to the minus 1. And if you remember, we can rewrite tau h theta in terms of tau h naught, right? We can say m equals tau h naught, what? Yeah, to the secant theta, right? Times tau h naught minus 1. Right? And we wind up with m equals tau h naught secant theta plus 1. Oh, minus 1. All right, then if we take the secant theta minus 1 root of both sides, we wind up with tau h naught equals m to 1 over secant theta minus 1. That's the equation that's presented in the book. All right, now the LU term, we do similar thing. That one's actually a bit easier. We got that? All right, what we wind up with there? We had the intercept term, which was LU h theta minus that slope term, which was tau h theta over tau h naught times LU in the vertical direction. All right, so again, we could put the upward radiance term at the angle in terms of the upward radiance term at native viewing position, which is just LU h naught secant theta minus tau h theta over tau h naught times LU h naught. All right, then this term right here is the slope. So we can do LU h naught secant theta minus m LU h naught. And then what do we do? We can factor out that LU h naught times secant theta minus m all equals b, and then we can just rearrange and solve for that. LU h naught equals b over secant theta minus m. So, again, what did we do? Well, we took a picture of several targets at two different angles, at the same altitude. And with just those two observed sets of values, you can wind up with, plotting those against one another, figure out the slope and the intercept, and then derive the path radiance and the transmission curve. So again, you calibrated your atmosphere for that particular position, and all you did was, as you flew over your target, you took your image, you continued flying, right? Because you got to turn your aircraft around anyway. But when you were a little farther away, you looked back at that same target and took another picture. Right? So by taking that second picture through a different path to the atmosphere, that angular path, you could then go ahead and derive your tau and u tau. Right. You can go ahead and do your downwelling radiance in the same way as you did for the profile technique. Once you have those other terms, you can go ahead and compute your downwelling terms the same way.
So this one is much easier, just because you don't need to
Fly at multiple altitudes. Absolutely. Absolutely.
So the first one is even accurate in the whole part, because it takes time for you to fly over many times, and at that time the atmosphere may change.
The sun angle changes.
Right.
The atmosphere changes. Yes, you can have a lot of change that goes on. Here, you could do it from the same flight line, and in that case, you reduce the amount of time way down. So for the Canadian officers, you know a guy named Art Burns? Or is he way too old? I went through grad school with him. He was a Canadian officer. I went through. He's got to be way retired by now. He came up with this thing. That was his paper.
Which one?
The multiple view angle. All right, now, one last technique, the multiple bandpass technique. Right. Multiple bandpass technique is, like I said, you look within an atmospheric window and subdivide that atmospheric window with sensors looking in those subdivided bandpasses. Okay, so let's say maybe 10 to 11, 11 to 12 microns. If you have a sensor in each of those bandpasses that's sensitive in just that wavelength region, essentially a two-band system, you can do the following. All right, we're going to rewrite the equation a little bit here. All right, we're going to say the radiance reaching the sensor at some angle theta is the radiance leaving the ground in that direction times the path radiance in that direction. Now here's a term that we haven't used before, LTA. Right? What this stands for, this is the temperature of the air column between the ground and the sensor. So it's a mean average temperature of the air column between the ground and the sensor. Okay? We're going to multiply that by this term, 1 minus tau h theta. Right? What is that? It's the emissivity of the atmosphere. Right? This is the effective emissivity, or mean effective emissivity of the atmosphere between the ground and the sensor. So if you know the radiance leaving the atmosphere due to its temperature, multiplied by its emissivity, this is the upwell path radiance. Right? Another way of looking at it. All right, so if you remember, we could write transmission as e to the absorption cross section, or extinction cross section, I'm sorry, times the number density of a particular molecule that we're looking at, times the path length over which we're looking. All right, you could approximate that with the Taylor series. So you can approximate this exponential as 1 minus that extinction cross section times number density times. So if you substitute all that back up here, we get this equation down here where we have the ground leaving radiance minus the ground leaving radiance minus the radiance due to the atmosphere, and multiply that by the cross section times the number density times the path length. All right. So what do we do? I don't like this thing. All right, here's why. All right, at this point in this paper, I forget who the author on this particular paper was. He goes ahead and he makes this assumption that he says that if you look at the difference between this equation here, right, these are temperatures. These are T's. Same equation, but these are radiances. Okay? So in the paper, when you read through this, it uses this sentence which is sort of weird. It says, expanding the Planck radiation equation, or radiance equation, about temperature and keeping only the linear terms. So if you went in and at all these locations, you put the Planck radiance equation, right? You put it here, you put it here, you put it here. That you could just keep the T's. Now, maybe that's true. The lambda's the same. All the constants are the same. And whether or not that really comes down to just this, I'd have to convince myself of. And I didn't do that last night. I should have done that last night. But if you substitute the Planck equation there, this doesn't really feel warm and comfortable to me. And here's why. They've used this sign, right? It's not an equal sign anymore. But maybe this is approximately true. And that's a big assumption on this technique, that you can just substitute in temperature. So T naught is the temperature of your target. So what they're saying at this point is that you can measure the temperature in band 1, measure the temperature in band 2, multiply the temperature in band 2 by the ratio of the extinction coefficients, divide that by 1 minus the ratio of the extinction coefficients, and you get back the temperature. Okay. There's just something very large here that bothers me. Okay. And I'm going to steer you away from this technique if I can. Right? People don't use this one all that often. It's referenced out there as something that people want to change. And really, what do you do in the final implementation? Well, you find two band passes where the extinction coefficients for those band passes are dramatically different from one another. Okay? And you plot as a function of extinction coefficient, so you have to know the extinction coefficient of the atmosphere, okay, which is something difficult to come up with. You plot that you plot temperature as a function of that, and then your intercept term for that plot winds up to be your surface temperature. Okay. Again, there's way too many assumptions in this particular technique. Now, I don't want to say that this is right, but a couple years ago, we put out a paper in the lab, Dave Messenger, myself, and Natalie Sinscali, and Marvin Blooming, another PhD student, undergrad student, and Dave and myself put out this paper called 3-band temperature extraction from reservoir treatment in precise atmospheric health. We think this was a really good approach that we took. It was a lot more involved, for sure. Where's that? Huh.
On the left, it's got full text PDF article resources.
Where is it?
Left of where your cursor's up.
Oh, okay. Ah, all right. So, I guess you got to be an American Geophysical Society member to do this.
If you Google Scholar, you can probably find it.
You can probably find it somewhere. Yeah, and I have copies of it too. We used 3 bands to come up with an answer, and we did this for a particular reason. There was a customer who wanted to know if they added a 4th band if they could do better, or a 5th band if they could do better. How many bands until you stop their well? Turns out that we thought there was only 3 to come up with. So I gave you a copy of that paper. I don't want to go over it in class because, to be totally honest, I've not had a single question about this paper from anybody in the community, and I've never seen anybody reference it. Right? Usually that says something about your work when nobody references it and nobody asks you a question. Either people are just totally blowing it off, or they don't understand it, or nobody cares. Right? It could be any of those 3 things. So I don't know what the right answer is. So I don't want to present that yet. But I do want to caution you that these multiple bandpass techniques are used extensively. This is what's on a GOES satellite. There's 2 thermal bands, right? Why is there 2 thermal bands? It's to do this atmospheric calibration technique. Okay? That's why those 2 bands are there. A big part is removing that atmosphere and getting to sea surface temperature. So, but in that case, we're looking at a very well-known target over a very well-known atmosphere. It's a maritime atmosphere, so you know the extinction coefficients, you know the aerosols that are in the atmosphere between water and the sensor. Over land, this works it's a lot harder to use this technique. So I would say, if you're looking for an in-scene technique, the multiple altitude or the profile technique is a great one, and the multiple angle technique is another great one. There is one downside to the multiple angle technique. You mentioned that it was a lot easier to do, and I agree. But you have to know the angular emissivity of your target, right? As opposed to just knowing the normal emissivity of your target. So you have to know BRDF to do multiple angle.
Or assume that everything is inversion.
Or assume that everything's inversion. Yep. Okay. So, any questions? All right. Just a reminder, I have to travel next week. I have to go out to the Electronic Imaging Conference in San Francisco on Tuesday and Wednesday, and we have an exam on Thursday. So next Tuesday there won't be a class, and next Thursday I'm going to ask Monica if she can come down and give the exam. Right? So we're 1 lecture away from the next exam. We've not done a lot since the last exam. Right? This timing for this one is a little sooner than I would have liked it, but primarily what's gonna happen on this exam is gonna be questions on calibration techniques. And there might be a couple, a question or two on the sensor designs that we talked about. But I think these are gonna be the most germane. So read, just make sure you read through the, I think we're up to section like 7.3 in chapter 7, goes through the thermal calibration. We'll finish up thermal calibration on Thursday, and we'll start to do reflective calibration at that point too. So, probably most of the material for the exam will be 7.1 through 7.4 or so in the text. So there won't be a lot of material that you have to study.
We're responsible for these equations, and being able to plug into them, or just understanding the technique?
Well, here's the beauty, right? These are really simple equations in the sense that, yes, you can memorize it, but I think more importantly, in 5 minutes you can derive any of these equations. Right? The downwelling gradients one, I think, takes a little while. But that might actually be a good question in itself, derive the downwelling gradients. But I think, if I were to give you, some data and ask you to come up with the transmission and path gradients terms, for instance, for a particular situation, and ask you to use the profile technique, if you didn't have them in your head, I think just what I want you to do is read through it enough times, look through the notes, ask me as many questions as you need to. I want this to be an intuitive derivation for you, so that you can just sit down and if you did forget the equations, just derive them out real quick. So it won't be a long exam, so you should have time to do that. So I haven't made it up yet, but
no formula sheet or anything like that, right?
no, I think there's. Believe me, I don't know any of my calculus anymore. I can't do math any longer. I just write code to do it. And I sat down last night just flew through these equations real quick. And I think everything here is just rearranging terms. You do a little bit of algebra, so you come up with this stuff. The key is just to know your first governing equation, right? As long as you remember this, you're halfway there. Especially for the thermal stuff. The reflectance terms, we're going to add a couple other terms in there. All right, so I'll see you on Thursday. Yeah, if you are running into problems on the lab still, make sure you get in touch with Monica and so we can fix it and send out things. People who are doing it early, I don't really need debuggers, but I do appreciate it.